For decades, standard database design has relied on a single dominant architecture, the 1970s relational model. In this system, information is organized strictly into flat tables made up of atomic attributes. Every intersection of a row and a column holds exactly one piece of data. This clean, simple representation is highly effective for standard business logic and administrative tracking. If you need to log employee names, salaries, and department codes, a two-dimensional grid provides a mathematically sound foundation for data access. But modern data is rarely that uniform. When a system attempts to store set-valued attributes, like an academic history or an employee's multiple children, or model ISA hierarchies, where a student is also a person, the strict grid becomes a bottleneck. To force this complex information into flat tables, developers rely on artificial keys to link isolated pieces of data across dozens of specialized junction tables. Retrieving a single real-world entity requires the database engine to execute heavy, expensive join operations to stitch those isolated rows back together. The traditional grid strains under the weight of complex networks. To handle hierarchical and multi-layered information efficiently, we must move toward two advanced storage models: object relational databases and native XML storage. The Object Relational Database, or ORDB, stops trying to flatten information. Instead, it models real-world objects directly within the database schema. This is achieved using object types. We define a client as a complex container. This container holds standard data types while also encapsulating other objects, like a dedicated address object that contains a street, city, and zip code. This is a comparison between a standard relational schema and an object relational schema. We can embed entire one-to-many relationships directly inside the parent object using collections. Instead of keeping a client's investments in a separate table, we define a nested table, allowing the client object to hold an unlimited list of investment records internally. While nested tables handle unlimited records, a different collection type called a vare is used for bounded lists. If a stock is traded on a specific maximum number of exchanges, say a strict limit of 5, a vare stores those exchanges directly inside the stock object itself. When we need to query this embedded data, we use the table operator. This command unnests the collection on the fly, flattening the nested table into readable rows for the query output. By physically nesting related data inside single objects, the database retrieves the entire hierarchy in one single pass. By co-locating this data, the system bypasses the specific computational costs associated with multi-table key matching and join execution. Beyond grouping structural data, an ORDB also groups the behavioral logic that acts upon that data. Rather than storing PL/SQL scripts separately from the tables, the logic is encapsulated directly inside the object itself as a member function. For example, if we need to calculate the yield of a specific stock or determine a price conversion, we build a function specifically for the stock object type to perform that calculation. This code block displays the exact PL/SQL syntax used to create a type body. The type body houses the implementation of the member function, in this case, calculating a price in yen based on a given exchange rate. Inside the function, the system uses a built-in variable called the self parameter. This denotes the exact instance of the object currently being invoked, allowing the function to pull that specific object's unique price. These functions are executed right inside a standard select query. Using dot notation, a user calls the function alongside standard columns, applying the logic instantly to every object in the result set. This approach aligns database architecture with software engineering principles. Structural attributes and behavioral methods are bound together into cohesive units. Strict object types are powerful, but they still require a predefined structure. When dealing with semi-structured data, like a web catalog where a shirt has color choices but a hat does not, rigid object schemas fail to accommodate the unpredictable attributes. For these scenarios, databases utilize native XML storage. Instead of tables or objects, the data is stored as a document object model, or DOM tree. a single root node branches downward into a hierarchy of child nodes, individual elements, and specific descriptive attributes. Querying this data requires a different mental model. You are no longer filtering flat rows in a table, you are traversing a hierarchical graph to locate specific target nodes. To navigate this graph, developers use a language called XPath. It allows a query to start at the root and execute steps along various axes to find the exact sequence of required nodes. This list shows SQL statements interacting with an XML column. By calling the built-in .query method on the XML document, the database executes XPath navigation strings directly within a standard select statement. Looking at the path expression, the syntax directs the engine to find all product nodes, regardless of their depth. It then applies a filter, represented by the brackets, to isolate only the products where the department attribute equals WMN. XML allows databases to store and query highly variable information dynamically, removing the need to enforce a rigid, prior schema on unpredictable data. While XPath is effective for navigation, it has limits. To perform complex functional iteration and transform the XML data on the fly, databases utilize a broader language called XQuery. XQuery relies on a specific structural syntax known as FLOWER. This stands for for, let, where, order by, and return. It functions as an analytical loop for semi-structured data. This query demonstrates a complete FLOWER expression acting upon our XML catalog. It combines iterative loops with variable assignment to manipulate the underlying nodes. The logic begins by iterating over every product node. The let statement assigns the product's number to a specific variable, marked by the $sign. From there, the where clause acts as a filter, restricting the sequence to only those numbers greater than 500. Finally, the return statement takes the filtered data and constructs new XML around it. It wraps the resulting numbers inside an item tag before outputting the final result. FWLOR expressions effectively bring the analytical power of SQL to hierarchical graphs, allowing for real-time data transformation without altering the source document. Regardless of the data model, relational, ORDB, or XML, the retrieval of data is ultimately governed by the physical limitations of disk I/O and CPU processing cycles. To handle these operations, the database management system takes the written query and converts it into a tree of algebraic operators. It then evaluates multiple alternative plans to find the most efficient execution path. This document shows how database administrators verify that efficiency. By executing an explain plan, the system reveals the optimizer's generated query path, showing the precise CPU and I/O cost metrics for every step. The query optimizer consults system analogs for statistics to estimate the size of the result set. If the calculated hardware costs are too high, the administrator may create an unclustered B+ tree index on the heavily searched columns. Applying a B+ tree index alters the engine's physical access path. Instead of reading thousands of pages sequentially in a full table scan, the engine traverses the index tree to pinpoint the exact location of the target data, reducing the total input and output operations. Query optimization ensures that high-level data abstractions execute efficiently, preventing complex logical designs from triggering unsustainable hardware costs. The era of forcing all enterprise applications into a uniform, flat table is over. Modern data engineering matches the architecture to the information, evolving from rigid grids to handle multi-layered complexity. Object relational schemas encapsulate structural data and behavioral logic into single units, utilizing nested tables and arrays to reduce the processing overhead inherent in relational joins. For semi-structured information, XML data types provide the flexibility to parse and transform unpredictable tree hierarchies without strict column definitions. Underneath these structures, the query optimizer relies on algebraic trees and indexing to retrieve this complex data with minimal hardware cost. Effective database engineering requires aligning the physical storage structure with the real-world complexity of the data it represents.